Let's go back to our roadmap and look at the next topic that we'll be covering. We're going to focus next on integers and floats, the representation of numbers in memory. That's going to be an important precursor before we can look at all the instructions for manipulating data values. So this section is going to cover the representation of integers, both signed and unsigned, and how we treat integers in C, talk about some shifting and sign extension operations that'll be important for arithmetic, and then we'll close with a section on floating point numbers. Basically, how do we represent binary numbers that are fractions rather than just integers. And then we'll get into a little bit of detail on the IEEE floating point standard for floating point numbers and how we do floating point operations and the rounding that they entail, as well as look at floating point numbers in C. There's a lot more to floating point numbers, and we will leave a lot of those topics to the text to cover, but we will do some of the basics. But before we get to integers, I just wanted to talk about encoding problems in general. So suppose we have a 52 card deck. The typical playing card setup with 13 cards of each suit, organized into 4 different suits, and we want to figure out how to represent these in binary numbers. How do we use zeros and ones to represent all these cards? Well, we could start by thinking about the operations we want to be able to do on the card. So we probably want to be able to tell if a card is higher than another or if they're the same suit. That might help us think about the kind of encoding we have. Let's take a look at some examples. So here's a very simple encoding to start with. We have 52 different cards, so let's use 52 different bits with the bit corresponding to the card that we have set to 1. So that would let us use 52 bits of a 64-bit word, let's say, in what's called a one-hot encoding, and meaning that there's only going to be 1 bit set to 1, all the others will be set to 0. So we can have the first bit represent, let's say, the ace of clubs, okay, and the next bit represent the 2 of clubs, and so on. What are some of the drawbacks of this? Well, it's going to be really hard to compare values in suits because we have individual bits throughout those 52 where we have to look at for the value and suit of the card. And we have a large number of bits to represent one card, an entire 64-bit word. This is called a one-hot encoding where only 1 bit is on. Another possibility is to do a 2-hot encoding where we might use 4 bits to represent the suit and another 13 bits to represent the 13 possible values of the card. So now 2 bits would be set to 1. So the first bit in the suit might be set to indicate the suit clubs, and the first bit in the value might be set to indicate an ace. Okay? So now it's a lot easier to tell if 2 cards are the same suit because they'll have the same 4 bits here. And we can tell if a card is greater than another by looking at the position of the 1 in the remaining 13 bits. But that's still a bit cumbersome. It's easier to compare suits and values, but it's still a large number of bits, in this case 17. This is what's called a 2-hot encoding now because we have 2 bits set to 1 for each card. Let's continue with this exercise and look at 2 possibly better representations. We could just do a binary encoding of all 52 cards. We only need 6 bits to represent 64 different numbers, so we can take care of 52 in just 6 bits. That would allow us to fit a card into just a byte and use the low order 6 bits to do that. So that's kind of nice. It all fits in 1 byte, and it's much smaller than the 1 or 2-hot encoding. But how can we make the value comparisons easier? The suit comparisons easier. We're still going to have all the cards numbered from 1 to 52, and that will not make it easy to do those comparisons. So we can do something that's a bit of a hybrid. We can use 2 bits for the suit, 4 bits for the value. 2 bits for the suit because we have 4 possible suits. So we need 4 possible binary bit patterns here, 0, 0, 0, 1, 1, 0, and 1, 1. And then 4 bits for the value, because the card can be anything from an ace to a king, 13 different values. Okay, so this makes it now easy to still do that suit comparison and just check if a number is smaller or greater than another for the value. Okay, so let's take a look at how we would implement these operations if we were doing it in C. So if we wanted to check if 2 cards are of the same suit, what we would do is have 2 bytes representing each card, okay? Maybe an array to represent a 5-card hand. We would take 2 cards out of the hand and ask if they're the same suit. And this function, same suit P, is implemented here below. It returns a Boolean value, just 0 or 1, and takes the 2 cards as arguments. What it does, you'll notice, is it takes the first card and does a bitwise AND with the suit mask. What is the suit mask? The suit mask is a special value set to hex 30. Why hex 30? Well, that corresponds to 0011 0000. You'll notice that when we do a bitwise AND with this mask, we will only have non-zero results for these 2 bits. All the other bits will necessarily be 0 because we have a 0 here, and 0 ANDed with anything will result in a 0. So this will essentially extract the value of the suit from the card representation. It will only have a non-zero value possibly in these 2 bits. Okay, so then we can do an exclusive OR with the suit of the other card. Okay, and why do we do an exclusive OR? Well, remember, an exclusive OR says either one is true or the other is true, but not both. Okay, so we would only get a perfect 0 result if these 2 suits matched exactly. In other words, they had the same 0s and 1s in these 2 locations. If they have that, then the result will be all 0s. And that's a Boolean false, and by taking the complement of it logically, we can say then that those 2 cards match, that our result is true. Okay, so what we actually implemented here was the opposite of the XOR by using the NOT. In other words, we said, rather are the 2 suits different bits, we're asking, are they the same bits, by just doing the complement of the XOR. All right, that would have been the same as saying this using the equals equals Boolean operator that says these 2 things exactly match. I just showed you what we can do with the Boolean operators. All right, let's take a look now at comparing the values of 2 cards. Again, we have our array of 5 cards, our hand, and we compare 2 cards, card 1 and card 2. So which has the greater value? Is card 1 a greater value than card 2? So you'll notice here what we're going to do is apply a different mask to the card. This mask is value 0F, the value mask. It has a 1 in the low order 4 bits. So we're getting the low order 4 bits which represent the value and zeroing the suit. And the way we get the suit zeroed is by applying the logical AND with a mask that has 0s in these positions. So now the result will necessarily be 0 there. And if we compare one of those extracted values to the other, we can simply get the greater relationship between the 2.